Okay, in order to make this easy and so that you don't have to read my horrible handwriting as much, I have gone ahead and written the answers in these boxes over here on the side, and then I'm just going to drag the appropriate box to the appropriate graph here. So I'll give you a chance to type this in and write this in on your notes at the end after I've done finished explaining. And so if you look here, continuity in non-technical terms means that a function is continuous if you can draw the function without ever lifting your pencil off the page. And that's kind of an elementary definition. Once we get to calculus, we're going to have a much more mathematically rigorous definition. But for now, this definition is going to do just fine. And it's an intuitive way to think about it, that if I can draw it without picking up my pencil, we call that continuous. So I want you to look at these four graphs and tell me which one of them you think is continuous. Which one of them, of the four, can you draw without ever lifting up your pencil? And hopefully you had a chance to think about it, and you said that the bottom right graph is the one that is continuous. That graph can be drawn without ever picking up your pencil. Now that means that these other three graphs all have something wrong with them. Two of them are non-removable discontinuities, and one of them is a removable discontinuity. A removable discontinuity, I'm going to define that first. A removable discontinuity is a discontinuity that can be removed simply by inserting a point where one is missing. And so which of the three remaining graphs would you say could be made continuous if we just inserted exactly one point? And hopefully you said that top left graph is the one that we could make continuous just by inserting that point right there. If we filled in that hole, so to speak, that would give us a continuous graph. Now, that leaves us with two more options. Both of these are going to be discontinuous and non-removable. One of them is called a jump discontinuity, and the other is called an infinite discontinuity. And hopefully you can look at these and figure out which one of them is a jump. A jump is where you're riding along on a graph, you're riding along, and then all of a sudden you just jump to a different portion of the graph. And so this bottom left is called a jump discontinuity. It is non-removable since we can't fix the discontinuity just by moving a single point. We would have to move an infinite number of points. All of this would have to be moved up to connect to that in order to make it continuous, and that's not just one point, it's many points. And so hopefully, by process of elimination, you understand that this top right graph is called an infinite discontinuity, and the reason for that is because it has an asymptote. That vertical asymptote there indicates a non-continuous function. It is non-removable, and we more specifically call it an infinite discontinuity. Okay, so I would go ahead and pause the video if you haven't already, and write in your answers on your notes to these four graphs. Okay, the next thing we want to discuss is increasing and decreasing functions and how to write the intervals for when a function is increasing or decreasing. And there are technical definitions for this, but we really just want to kind of keep it simple here and remember two things. That the first, we have to read the graph from left to right, and secondly, whenever we report intervals of increasing or decreasing, we always use x values. We use the x values. Everybody say that with me. X values. So the y values here are going to be irrelevant. We don't care about the y values when we report increasing or decreasing. We only care about the x values. So from this graph, what intervals is the function increasing, decreasing, and constant? So I'm going to start with increasing, and just the basic definition of increasing, which means that the graph is going up from left to right. So starting at x is equal to 0, we are here at this point, and the graph starts by going down. So this is actually going to be an interval of decreasing. Why don't we just go ahead and write that? since we're there. And so this is going to decrease on the interval from 0 to 1. And I'm going to write those as open intervals. You can write them as closed intervals. There's sort of a big debate in mathematics whether we should have them open or closed or maybe some combination of the two. I'm not concerned as much about that in this class as I am with just making sure you get the correct intervals. So whether you report them as open or closed, I don't really care at this point, but what I do care about is that we have the correct intervals. Now, is there anywhere else that we're decreasing? We'll maybe come back to that. Let's just keep reading the graph from left to right. So starting now here at 1, what's happening from 1 to 2? Is the graph increasing or decreasing? Well, hopefully you said neither one. And so if it's not increasing or decreasing, that means that the graph is constant. And so the constant interval is going to be from 1 until 2. Now, starting at x equals 2, what's happening to the graph? It is at this point, and it starts going up, and it stops going up whenever we get to this asymptote. Notice that there's this asymptote, vertical asymptote at x is equal to 3. And so when we write the increasing interval, we're going to start at 2 and stop at 3 because the 3 is a point of discontinuity. Now, after 3, you got to be really careful. This arrow is a little confusing. You got to remember that we're reading the graph from left to right. So starting from left to right and following along with your pencil, what is happening to the graph? Hopefully you said increasing. So this is going to now go here, and I'm going to have another interval of increasing, and that's going to be from 3 until 4. So remember, read the graph from left to right. Use x values, not y values. The y values are irrelevant. It's only the x values that we care about when reporting increasing and decreasing. Okay, when we discuss boundedness, what we're really talking about is the range. And so I'm going to give you a second to pause the video, write in these definitions just real quick. And so now that you've done that, I want to give you an example of what each of these looks like. And so if you think about bounded below, what does it mean for a function to be bounded below? It means that a horizontal line can be drawn below the graph. So for example, what I mean by that is that if I have, let's just say, a quadratic function that looks like this, that function is bounded below because I can draw a horizontal line that basically acts like the floor of the function, and the graph doesn't go any lower than that horizontal line. So hopefully that's making sense what bounded below means. Bounded above is just the opposite. So for example, if I had an upside down parabola that looked like this function is bounded above because I can draw a horizontal line that is above the graph, and the graph does not go any higher than that horizontal line. And then bounded is just a combination word that means both bounded above and bounded below. So we're going to discuss a function in the second part of this class called the sine and cosine graphs that is a bounded function, and the reason for that is because it looks something like this, like a wave, and it goes in this direction also, and this is a very rough drawing, by the way, but I can draw a horizontal line above that graph, and I can draw a horizontal line below that graph, so it is both bounded above and below, and therefore it is called just simply bounded. Okay, when we discuss local and absolute extrema, we got to define what these words mean, and this is one of the more technical things that we'll talk about. But extrema is just a plural form of one extreme value. And you think about, what does extreme mean? High and low, right? If I'm extreme, I'm either on one end or the other. I'm either really high or really low. And so that word extreme or extrema, the plural version, just means maximums and minimums of a graph. And so when we talk about local or relative extrema, those two words are used as synonyms, so they mean the same thing. Local or relative extrema are y values that are bigger or smaller, depending on if we're talking about maxes or mins, than the other y values on an open interval. So than all others on an open interval. And so the reason I define it that way is because in order to have a local or relative extrema, that's got to be the biggest point, and you've got to be able to draw an interval around the point. And I'll explain what that means here in just a minute when we get to the example graph here. Now, absolute extrema, that just means that it is the biggest, not just on an open interval, but on the entire graph. So absolute extrema are y values bigger if we're talking about maximums, or smaller if we're talking about minimums, than all other y values on the entire graph. So sorry for the bad handwriting here, on the entire graph. And so we're not just concerned with an open interval around a particular set of just a few points, but we're concerned with the entire graph itself. And so we're going to label each of these 5 points here as either a relative max, an absolute max, a relative min, or an absolute min, or, as we're going to see in one of the cases, none of those. And so let's just start with f of a. And so f of a is this point right here. Now, this point cannot be a local or relative extrema. And the reason for that is because I cannot draw an open interval around it. If I try, there's no portion of the graph over here on this side. There's no left-hand side of that point. And so that's why I cannot call this local. Now, can I call it absolute? Well, I can if it is the smallest point on the entire graph. So if you just look here, if I were to draw like a little horizontal dashed line across here, is that the smallest point on the entire graph? Hopefully you would say it is. And so this is called an absolute minimum. Again, it cannot be a local minimum because there's no open interval around it. There's no left side to f of a. But it is the absolute minimum because it is the smallest y value on the entire graph as we see it. Okay, if we go now to f of c, can f of c be a local max? Yes, it can, because I can draw an open interval around f of c, and there is a left and a right side to f of c. So it is a local maximum because it is the biggest y value on the open interval that I just drew. Now, is it the absolute max, meaning it is the biggest y value on the graph? Well, the answer to that is no, because if you were to draw a line across here, you can see there are y values that are bigger than f of c. But in that little tiny neighborhood on that open interval, it is the biggest one. And so we can call it a local, or relative, if you want to use that word, local max. Okay, going to f of d now. Can that be a local min? The answer is yes, because I can draw an open interval around it. Is it the absolute min? Well, no, it's not, because we already said that f of a was the absolute minimum. And so therefore f of d is just simply a local or a relative min. Okay, going to f of e. F of e would be this point right here. Now that's a high point. Is it a local maximum? Well, yes it is, because we can draw an open interval around it. There is both a left side and a right side to it. So it is definitely a local max. Is it also the absolute max? Are there any y values on the entire graph that are bigger or larger than f of e? And the answer to that is no. It is the largest point on the entire graph, and so it is also the absolute, and I'm going to abbreviate just because I'm running out of space. It is also the absolute maximum. Okay, finally we have f of b. And f of b, can that be a local max or min? And hopefully you said no, because I cannot draw an open interval around it. There is a missing piece over here on the right-hand side. It does not have a right side to it, if you will. So it cannot be a local max or min. Is it the absolute max or the absolute min? Hopefully you said no. We already have an absolute min. We already have an absolute max. F of b is nothing. We'll just say neither. It does not fit any of the categories that we are talking about. Okay, the next thing we want to discuss is symmetry. And so symmetry is something you've kind of been talking about for a long time. It just means that the function looks the same on one side as it does on the other, and we're primarily concerned with two different types of symmetry. The first one is symmetry with respect to the y-axis. And so what does this look like graphically? If I have, let's say, the square root function that looks like this, what does it look like to draw something that's symmetric to the y-axis? Well, the y-axis is here, and so that means that we would have the piece of the graph that would go in quadrant 2 over there on the left. And so that's what something symmetric to the y-axis would look like. What does it look like numerically? Well, let's just say we have the point here, and let's just call it the point 4, 2, if we're talking about this being the square root graph. That means that we would also have the point -4, 2. It's got the same y value, it's got the opposite x value. And so we would say f of -4 is equal to 2, and so therefore f of +4 is also equal to 2. And so what does that look like algebraically? Well, what I notice if I try to generalize this is that if I have f of +x, that's got to be the exact same thing as f of the opposite of x. Okay, so you're going to want to remember that definition. F of x is equal to f of -x. That's how we prove that something is symmetric to the y-axis. And most importantly, or at least equally as importantly, we say that these types of functions are even. Functions that are symmetric to the y-axis are even. Now, symmetry with respect to the origin means that if we have this square root function once again, and we'll put that same point on there of 4, 2, that we're also going to have the piece of this that is symmetric to not only the x-axis, but also to the y-axis. And so what's the point that's going to be on there? It's going to have the opposite x-coordinate and the opposite y-coordinate, -2 there. Okay, so numerically, what does it look like? We are going to have, let's just say if we have f of +4 is equal to +2, then that means that f of the opposite of 4 is equal to the opposite of 2. And so algebraically what we have then is if we have f of, let's just say, the opposite of x, that this is equal to the opposite of the original y value, f of x. And so we call these functions odd. Anytime something is symmetric, whoops, let me do that with a highlighter. Anytime we say that a function is odd, that means it has symmetry to the origin and vice versa. Any graph that has symmetry to the origin is also called odd.